Good morning or good afternoon to everyone. I am Gabriele Malgaroli from Politecnico di Torino, and my research activity is titled Innovative Model based on the irradiance temperature fitting of equivalent circuit parameters for commercial photovoltaic modules towards accurate power and energy prediction. And I am currently a PhD student in Electrical, Electronics and Communications Engineering at the Energy Department of Politecnico di Torino. The activity carried out during my PhD course aims to propose an innovative model to predict the power and energy generated by photovoltaic modules with higher accuracy with respect to current models, using the parameters of their equivalent circuit. This activity will be furtherly developed in the next years, and this model will be used to perform a real-time detection of defects by the inverters. The performance of PV generators can be described using proper equivalent circuits, and one of the most used consists of 5 parameters. These parameters are affected by weather conditions, temperature and irradiance, and their knowledge in different weather conditions can permit to trace the current voltage characteristic curve of PV generators for any working condition. However, in literature, such a model is not currently available. The novelty aspect of this research is the development of an innovative model to predict the power and energy generated by photovoltaic modules, with higher accuracy with respect to current models. This result is obtained by defining optimized equations to predict the behavior of each equivalent circuit's parameter as a function of irradiance and temperature. In literature, some equations are provided, but some of their coefficients are unknown. In addition, some works propose numerical procedures to identify such coefficients, but two common issues regard the repeatability of the numerical process and the overfitting, which is rarely discussed. In this activity, proper experimental datasets and filtering techniques are used to overcome these issues. In this slide, the procedure used to identify the most important coefficients of the optimized equations is presented. First, datasets of measured current voltage curves are properly filtered to exclude curves affected by mismatch, measurement errors, or other issues. Then, the parameters are determined for each curve using proper numerical algorithms. Finally, nonlinear regressions determine the optimal sets of coefficients for the equations. Such optimized equations will be used to predict the generated PV power and energy with higher accuracy with respect to the most diffused model in literature. 7 PV modules from different technologies were tested in 2 universities using experimental datasets up to 1 year. A set of optimized equations was identified for each module, and these equations were used to evaluate the generated PV power and energy in the period under analysis. The results were compared with the experimental data and with the prediction using the Osterwald model, which is the most common PV model in literature. In this slide, the modules under analysis are shown. They belong to different technologies: conventional monocrystalline silicon, high-efficiency monocrystalline silicon, conventional polycrystalline silicon, and polycrystalline silicon with half cells, and have rated power varying in a wide range between 100 and 370 watts. In this slide, the comparison between the experimental data, red dots, and the optimized equations, blue curves, is presented for the photovoltaic current on the left and for the reverse saturation current on the right of one PV module under analysis. In this slide, the plots refer to the non-ideality factor, while in this case, the behavior of the series resistance is reported. Finally, the deviations from experimental data in terms of energy prediction are presented for the modules under test. The effectiveness of the proposed model, blue bars, is clear, and the optimized equations provide huge improvements with respect to the Osterwald model, orange bars, which is the most common model in literature. Regarding the second part of this research activity, electrical defects, mechanical defects or failures may affect the performance of PV plants, and the current diagnosis techniques are the infrared thermography and the electroluminescence. However, these methods permit to check the state of health of PV generators, but they are expensive since they require additional equipment, and a continuous monitoring of the systems is not possible. So the innovative model developed in the first part of the activity will be integrated in DC-AC converters. Actually, the inverters will acquire the current voltage curve of PV generators. They will extract in real time the parameters of the single diode model, and they will compare these parameters with reference values corresponding to healthy modules. These reference values will be estimated using the optimized equations of the innovative model. Nevertheless, for each PV technology and for each parameter of the equivalent circuit, a proper tolerance will be identified in order to distinguish between healthy and defective modules. Thank you for your attention.